Okay, we've been talking about CC double bonds as nucleophiles for making carbon-carbon bonds, and this is really the meat of modern organic synthesis. In some way, shape, or form, whether you're using transition metals or enolates or other fancy atoms that are not in the second row, CC double bonds, pi systems as nucleophiles. And so this section really is about CC double bonds with lone pairs next door, lone pairs that donate into the CC double bond and amp up the nucleophilicity. So we spent our previous topics talking about bonds, long bonds that can amp up the nucleophilicity of the CC double bond. But lone pairs really, it's hard to beat a lone pair for making a CC double bond more nucleophilic. And we're starting off by talking about enols. Enols, not enolate anions, just neutral enols, and this idea that they are in equilibrium with carbonyls. And we call these isomers, where we move a proton onto the oxygen atom of a carbonyl, we call those tautomers. So this is the enol tautomer, and this is the keto tautomer. So a special kind of isomeric relationship where you're simply moving a proton from one place to the other. It can't be a resonance structure if you're moving atoms around. That's not resonance. And the mechanism for this reaction under acid catalyzed conditions involves a two-step process with protonation of the carbonyl. Okay, so much of organic chemistry is driven by the stability of carbon-oxygen double bonds. CO double bonds are stable. Carbon dioxide, global warming. You burn things, you get CO2. It has two carbonyl groups in it. So nature loves C double bond O, and anytime it can, nature will gladly trade a CC double bond for a CO double bond. So carbonyl groups will be stable when there's some sort of an isomerization that's possible. I want to go ahead and look quantitatively at the relative stability of the keto tautomers to enol tautomers. Right? If you just take a bottle of acetone in the laboratory, you can't stop tautomerization from occurring. It is occurring, and there are enols in there whether you want it or not. It's just a matter of what is the relative concentration of those two species at equilibrium. So I'm going to go ahead and give you some numbers here for the relative ratios of the keto tautomer, which is favored, and the enol tautomer. I'm going to start here with this middle example here, acetone. That's kind of like our canonical carbonyl group, a simple ketone. Let me go ahead and give you the numbers. The keto form is favored by how much? I'll tell you how much. It's favored by, oh no, we've lost our screen for a second there. By 100 million to 1, right? If you've got a flask with 10 to the 23rd molecules in there, 1 out of every 100 million of those molecules is the enol tautomer. And you don't get to choose that ratio. That's just a delta G right there. That's what determines that relative ratio. Now, what would happen to this carbonyl if you put a donor right next door? If you had a lone pair donor, okay, I'm so sorry for this screen thing. I don't even know what. Let me take a moment here to, like where, like maybe in this cable there's some sort of a break or something that's, I don't know. Like I said, I've tried 2 different HDMI connectors, and they both have the same issue. So I think it's in the cable here. Okay, so what would happen if you had a lone pair donor next door, like in an ester or an amide? I don't have the enol numbers for an amide, but that lone pair can donate into this carbonyl, and that's a stabilizing interaction. It makes the keto form more stable. I mean, why do you react with the keto form? Because it's almost like C plus on the carbonyl, but that lone pair helps to stabilize that. And so it changes this ratio. I don't know what the numbers are, but it is much, much more stable than 100,000 to 1. So the keto form is much more stable. I'm just putting 2 greater than symbols there. The keto form is more stable than in a simple amide. So harder to make enols, to have an isomeric amount of enols when you're talking about an ester or even worse for an amide. But just a simple ketone, 100 million to 1. There's not much enol in there, but there will be enol in there. Now why is it, what is it about the ketone that makes that keto form stabilize? There's something going on there that's not so obvious. There are CH bonds here on these methyl groups of acetone that are donating into the pi star system of the carbonyl. Now you might say, well, that's not a very strong donor. That's right, it's not a strong donor. A CH bond is not a strong donor, but those are the same CH bonds that stabilize a T-butyl carbocation. So it's not a fantastic donor, but it is better than nothing. So let me go over here and take a look at a functional group, an aldehyde, where we can see what it's like to have nothing on there. See that H right there? There is no bond sticking off this H that can donate into the carbonyl. There's nothing on the H that stabilizes that carbonyl. And so when we go to an aldehyde, it's not 100 million to 1 anymore. Now it's just 100,000 to 1. Much easier to enolize. Much easier to enolize aldehydes than to enolize ketones. Now, we can do something to stabilize the enol form. So what can we do to stabilize the enol form? If you look over here at this enol, wouldn't it be great if we had some sort of a pi acceptor here that could help with resonance with that oxygen? Right? If we could help that oxygen donate better, then we might be able to stabilize the enol side of the equation. And that's what happens when you have a phenyl group at the alpha carbon of a ketones. When you take alpha phenyl acetone, enolization is a big problem. When you try to do Grignard additions to phenylacetone, you just get a lot of deprotonation of the enol form to form enolates that you don't want in those reactions. Not easy to add to phenylacetone because of this enolization problem. I'll give you the numbers here. It's not 100,000 to 1. Now it's 4,000 to 1 because we're stabilizing that enol form. Let me go ahead and draw the resonance here. Right? It's wow and wow. Right? You can donate into, I got to finish the arrow. You can push those electrons all the way into the benzene ring. Now, the benzene ring is not a great pi acceptor, but it's better than nothing, right? There's a pi star system associated with the benzene ring, and so all that resonance there helps to stabilize the enol form. Let me show you another kind of a trick here that does two things. Boy, whenever I see two carbonyls right next door to each other like this, those carbonyls are super reactive. They're unstable when you have two carbonyls directly attached to each other on the carbonyl carbons. We call these alpha keto systems. This would be called an alpha keto ester. And when you put this extra carbonyl group, in this case it's an ester, right next to your carbonyl carbon, it's like you don't have a good donor bond anymore on this carbon. You don't have a CH anymore. You've got bonds to electronegative atoms. Those are not good donor bonds. So you don't have really a good donor. And there's a common estimate out there that a carbonyl carbon, like in acetone, has about 1/4 of a positive charge on it. Kind of like 1/4 of a negative charge on the oxygen of acetone, 1/4 of a positive charge on the carbon of acetone. So when you put two carbonyl carbons next to each other, like 1/4 of a positive charge next to 1/4 of a positive charge, that's destabilizing. So, but not only does this alpha keto group right here destabilize the carbonyl, it also, when you look at the enol form, has the opportunity to form this 5-membered ring hydrogen bond. So in this case, you get not only the destabilization of the keto form, you also get this hydrogen bond stabilization of the enol form. And so now we're talking about an equilibrium ratio of enol of 100 to 1. You know, probably 100 to 1, you're not going to be able to see that enol tautomer in your NMR unless you really zoom in to the baseline of your NMR. It's hard to see that, but there is enol present in substantial amounts. The last example we're taking is kind of extrapolating out on this phenyl trick here. What would happen if we put a good pi acceptor there instead of a crappy one like the benzene ring? Well, if we put a good pi acceptor here, right, over here, it'll really stabilize that enol form. Now when we look at this enol form, it has all the tricks going. It's got this great resonance stabilization here, where we can donate from that lone pair all the way into this carbonyl. It's got that hydrogen bond. Look at that hydrogen bond right there, H bond. That's awesome. So now we're talking about a serious pain in the rear if you're trying to take an NMR, because if you take an NMR of that compound, you'll see two compounds. And you can't purify one away. You will always see two compounds in your NMR. They are in equilibrium. There is nothing you can do. If you add acid, you can accelerate the rate that it reaches equilibrium. But in chloroform solution in an NMR tube, the equilibrium is already fast enough to where you can't stop yourself from seeing those two species present. Now notice, in none of these cases is the enol form totally favored. I'm going to show you an example of one compound. It's a class of compounds where the enol form is massively favored, and it is kind of the outlier here. I don't know if you can guess that. Take a guess. What's the one class of compounds where the enol is favored? That would be phenols, benzene rings, right? It's aromatic, so the enol is clearly favored here. I don't have to draw the keto form. It's just favored. I don't know the equilibrium value of the keto form. I've never heard of anybody observing or estimating the amount of keto form. So it's kind of obvious there. So aromaticity massively favors that enol form, not the keto isomer of a benzene, of a benzene ring, of a phenol. Okay, so enols, they're present, they're there. You can use acid to accelerate the equilibration between the two, but you can't change the ratio, the equilibrium ratios there. That's determined by free energy differences, free energies of formation, and you don't get to choose that with your catalyst. All right, so enol ethers. So what if we have an OR group on our alkene instead of an OH group? It's kind of similar reactivity, so let's talk about enol ethers. And the advantage of an enol ether is you could synthesize 100% enol ether, and there's no tautomerization here. So here's a very common enol ether that you'll see used in organic synthesis. This is called dihydropyran. A pyran ring is a six-membered ring with oxygen. And this is a commonly used reagent for adding a THP protecting group to an alcohol. So suppose you didn't want this alcohol to react. Suppose you wanted to make anions here, and you didn't want the alcohol to get in the way. You might protect that with a silyl group or a THP protecting group, a tetrahydropyran. So you add some dihydropyran, but you need to add a little bit of catalytic acid to accelerate the rate at which you form this mixed acetal. Let's go ahead and draw the mechanism for that reaction. So the mechanism is going to start off with protonation of something. We've got this acid in here. Let me go ahead and draw out our toluene sulfonic acid as an acidic catalyst. And you would not be crazy if you said, oh yeah, look at that oxygen. I'm going to protonate that oxygen. Van Rankin says to always start your arrow pushing with lone pairs. That's not crazy to protonate an oxygen atom. It's happening in solution, but I promise you, you will not get to the product if you start off by protonating the oxygen. Enol ethers are nucleophilic and basic here, on that carbon. On the carbon atom, that's where all the action is going to be. If I see an enamine, an enol ether, an enolate, all the action is on that end carbon. Those lone pairs are doing something. Don't use them to capture the proton. Use those lone pairs to push into the pi system, and that's why that yellow carbon is nucleophilic and basic. So when we protonate the system, don't protonate it on oxygen. I'm not saying that doesn't happen, but if you want to get anywhere with this, pick up the proton and put it on that carbon atom. And now once we do that, we've got an electrophilic species that looks kind of like a protonated carbonyl. So when I draw out this next intermediate here, I'm going to have this species that looks like this. And doesn't that look like a protonated carbonyl? That just makes me want to attack that carbon atom in that C double bond O. That's more reactive than just a neutral carbonyl. And so if I have some sort of an alcohol present in solution, right, ROH is still floating around in there. Now, that's going to just add right into that. No problem. Look at that. So we add into that system, we make a mixed acetal. We still have a proton we have to get rid of. So let's go ahead and draw that out, draw out that intermediate. And this is an oxonium ion. So I'll just use the conjugate base left over from my acid to pull that proton off. And that's how you make a THP protecting group or any mixed acetal protecting group. So notice we use an enol ether. And again, an enol ether, you can isolate, you can buy a bottle of that enol ether. It's not like enols, which are in equilibrium with the keto form. There's no keto compounds in that bottle of dihydropyran that you buy from the chemical supplier. Okay, let's take a look at another example of something that's kind of like that dihydropyran, but I would call this a vinylogous example, maybe in a way, of an acetal. So it's almost like there's this lone pair here on this oxygen, this example down below. There's this lone pair here on this oxygen that's trying to push out this acetate group that I've drawn below. I've drawn the Lewis structure for that acetate group. So in this reaction, they've added a Lewis acid catalyst to this. Stannic tetrachloride is a Lewis acid. It loves oxygen. So you notice they didn't run this reaction in methanol as the solvent. They're just using one equivalent of methanol. And if you put methanol in with stannic tetrachloride, the methanol will add to the tin. And then it'll come out. And then the methanol will add to the tin. And then it will come out. And then the methanol will add to, right? If you think that you ought to attack this Lewis acid tin with the methanol, that's smart. That's happening. Okay, but that's not going to take you anywhere. Let's go ahead and talk about how you get to the product of this reaction. Because eventually we need to make this group here, this acetate group down at the bottom, we have to turn that into a leaving group. And this sounds like a really good place for us to use our Lewis acid, that tin species. So let's go ahead and draw a lone pair here on the acetate leaving group. And we're going to use that, the carbonyl oxygen as our nucleophile. Now, if you wanted, you could start off with this lone pair and then push the electrons all the way, but I'm just going to use the lone pair that's already there on that oxygen atom. In fact, I don't really have room to draw all these steps here. I'm just going to go straight to the Lewis acid complex. So let me use I'm just going to use my eraser here, and I'm just going to go straight to the bond. So let's just say that there's a step that we're not going to show where we've coordinated with this tetrachlorostannic tetrachloride. That makes this STAN8 with a negative charge on tin. No problem having 5 bonds to tin. No problem having a negative charge on tin. And so now this now turns this acetate into a good leaving group. Let's go ahead and push the electrons down. Now this is a great opportunity for us to push down here, right? That enol, the enol ether is nucleophilic. And so let's use, where is it nucleophilic? Enol ethers are nucleophilic right here. So let's go ahead and use that I'll label it as yellow. Let's go ahead and use that yellow carbon as a nucleophile. We'll keep pushing with our arrows here and then push out the leaving group. And I'm going to use more than 3 arrows here, but there was a way to do this where we could have done it in 3 arrows if we just drew a resonance structure of that ester species. Okay, so now we've popped off this group, and we've got a powerful carbon electrophile in here. Look at this carbon electrophile. Now, at this stage, you wouldn't really know enough to know which of these 2 carbons is the nucleophilic carbon. And I'm just going to tell you, it's the one right next to the carbonyl that is the electrophilic carbon atom. And so now we could come right back in with our acetate that just left. That would be kind of pointless. It would just take us back. But now we've got that methanol in there. Let's go ahead and use the methanol. That's why they added one equivalent of methanol to the reaction mixture, because they wanted to make a bond here. So I'll go ahead and write methanol here. I'll move my H out of the way so I've got room for that lone pair. And now let's go ahead and attack this species, this oxonium ion. That makes our oxygen-carbon bond. And somewhere around we still have, I'm showing you that the product is going to be acetic acid, so I feel obligated to explain to you how we're going to get back to that. Let me go ahead and draw the other counter ion that's still patiently floating around. This is what happened to that leaving group. It left as this species, this tetrachlorostanate anion, this acetoxy stanate anion. And because of that negative tin, right, that whole pi system with the oxygens there is basic. So we can now use this. I'm not going to show all the steps in this mechanism, but I think you'll get the idea. I can use the lone pairs, right? That's more nucleophilic now that it has that tin minus next to it. And I'll use the carbonyl oxygen to pick off the proton. I'm trying to explain how I get to the acetic acid at the end of the reaction. And there's a couple, this is actually a 2-step process, and I'm not going to show the dissociation of the tin to regenerate the tin Lewis acid. But you could draw that out for yourself if you wanted to. So, right, initially you'd have a tetrachlorostanate here, and then it would come off and give you the acetic acid product. All right, so again, it's kind of like an enol ether here. This starting material is like an enol ether that pushes out that leaving group. This specific reaction where you start with what looks like a sugar derivative, and you have a leaving group here, but the nucleophile appears over here, is called a Fourier rearrangement. Notice that the leaving group left from down here, but the nucleophile added next to the ring oxygen. That's called a Fourier rearrangement. You can do that with carbon nucleophiles. Allocylanes will add to those same places. Here it's kind of boring. It's an oxygen nucleophile, methanol, but the same idea. Okay, so enol ethers can push out leaving groups, just like they can be used to get protonated, like we did up here. We protonated the enol ether. Okay, let's go ahead and, we've talked about enol, keto, tautomerism. Keto, enol, tautomerism. Carbonyl groups are way favored over CC double bonds. C double bond O, that's awesome, right? Except for that phenol example, the keto form is always favored. And we talked about imines and enamines before. We talked about the mechanism for imine formation when you start with carbonyl groups. You can draw a similar type of tautomerism for C double bond N. So over here, look at this system that we have over here. I've got an imine on one side. I've got the imine over here, C double bond N. And in the product, I'm kind of trading that for C double bonds. This is not a good situation, because neither one of these sides is favored. If you look at the equilibrium ratio of these two species, it's 1:3, right? If you want to isolate an enamine, what you have to do is make a species that can't undergo this tautomerization. So if you want an enamine, this would typically be what an enamine looks like. You put R groups on there that cannot be deprotonated to form an imine. That's what you do if you want an enamine. And likewise, if you want an imine, you'll start with amines that have only one R group instead of that H. So whenever you're trying to make imines, usually you've got enamines floating around. And if you're trying to make enamines, you usually have imines floating around. But really, usually the key functional group, if you're trying to add to these species, would be an iminium ion. We usually don't care so much about the neutral imine when we're trying to add the C double bond. We care about the iminium ion is the important one. Okay, but here we're talking about double bonds that have lone pairs next door. So let's go ahead and draw that. Look at that. Boy, if an oxygen lone pair can make that double bond more nucleophilic, think about how much more reactive is an enamine. An enamine is way more reactive than an enol or an enol ether. So how do we make these enamines? Well, we have to start off with some sort of a secondary amine. Pyrrolidine is a common one. Pyrrolidine is a common amine for making enamines. So notice over here in the product, right, there's not H's on there that we can deprotonate. You can't make a neutral C double bond N with these ingredients in our recipe. So what are some tricks what's the common trick? You got to find a way to drive the equilibrium here. Look at what's happening. We're trying to take a lovely looking stable carbonyl group like here and trade it for a CC bond. That cannot be good. It is not good. The equilibrium disfavors that product. If you want to drive the equilibrium, what we have to, man, I just touched that. If we want to drive the equilibrium, we have to look at the other mysterious product that you can't see. We have to get the product, water, the byproduct, and get that out of the reaction mixture. There's a couple of ways that we do this. The most common way, the most inexpensive way, is that we do these using toluene as a solvent. I don't know if you've learned this, but when you reflux in toluene, it's not just toluene that boils. Toluene boils up as a mixture with water. You can look up tables to find the ratios of water and toluene. It forms something called an azeotrope as it boils off. It carries water with it into the vapor phase, and as it condenses, you can condense it into a trap where the water separates out as a second layer. So forming an azeotrope, you have to remove this. So we have a special piece of glassware called a Dean Stark trap that allows you to trap out these mixtures of toluene and water, and the layers separate. So your water ends up in a separate part of the distillation apparatus. So you just have to remove water, and that will drive the equilibrium. Isn't that like Le Chatelier's principle or something like that? I usually think of adding an excess of something with Le Chatelier, but if you remove one of the products, you'll pull the equilibrium all the way over to the enamine side, and then you can isolate the enamine. But you can't just mix those together and expect to give up your great-looking carbonyl group. That's not going to happen. It's like the carbonyl group is the winner there. But removing the water takes the oxygen out of the reaction mixture as water. Okay, so what are some common enamines? Pyrrolidine you'll commonly see people making enamines using pyrrolidine. So there are some other common amines, and they have to be secondary amines that are used for forming enamines. Some of the other common ones would be morpholine. This would be a common one. So making morpholine enamines. Piperidine is a common one. We've already seen that used for making aminium but you'll see people making enamines using piperidine. So pyrrolidine, morpholine, that one with the oxygen in there, and piperidine. Those are the common amines, most common amines for making enamines. And enamines are just way more nucleophilic. Let me just admire these lone pairs here. Just souping up those out. Look at that lone pair right there on that piperidine, making that enamine more nuclear. Look at that lone pair on that morpholine. And they are souping up the reactivity of these enamines at this position, at this position, at that position. That's the reactive position. Just like an enolate, just like an enol ether, just like an enol. Let's go ahead and take a look at some reactions of enamines. This is what people used to use back in the 1950s before we had enolate chemistry. Nowadays, we don't use this so much anymore except in the field of organocatalysis, very powerful. But before we knew how to make enolates selectively, powerfully, people used enamines for CC bond formation. So when you take enamines, the key reactions here, well, I'm getting a little bit edgy here about what I'm saying because I know there's something else that's going on here, but I'll give you the simple story. The simple story is that enamines are nucleophilic here on this carbon, and you can use those for SN2 reactions with methyl iodide, with allyl bromide, benzyl bromide, reactive SN2 electrophiles where there's no possibility for competing E2 elimination. Those will give great yields of CC bond forming reactions. If you have alpha beta unsaturated carbonyls, these are great nucleophiles from Michael additions to enones. But you can see in this case, when you form that first bond, you'll end up with an aminium ion, and you'll have other basic species floating around. Some of the basic species could be HBr or other amines that are floating around. Something will pull that proton off, and in these reactions, you'll end up regenerating. Initially, you'll end up regenerating in enamine. I think we had a problem like this on our problem set. You could just write A- here or something pulling that proton off. I'll go ahead and regenerate the enamine. That's the initial product of the reaction. But later, if you come back in and add water to this system, almost nobody tries to re-isolate the enamine. But if you hydrolyze this by dumping water in there, and there's still HA left over from the reaction mixture, you're just going to get hydrolysis of the enamine and get the ketone. So way back when, this is what we used to do when we didn't know how to make enolates selectively and in high yield alpha to carbonyl. So we used to use enamines not in the 1990s, way before the 1990s. Let's go ahead and talk about the relative reactivity of these species. Enamines, imines, enol ethers. And so I'm giving you here the relative reactivities, right? Enol ethers are pretty nucleophilic because they've got that, I don't know what just happened there, because we got that we've got this lone pair over here on this oxygen that donates into that pi system, and it makes that enol ether, it makes the enol ether nucleophilic on that end carbon. Enamines are more reactive, by 1,000,000 times more reactive than enols or enol ethers. You should expect that. Nitrogen lone pairs are more nucleophilic than oxygen lone pairs. Oxygen's more electronegative. The oxygen lone pairs are not as nucleophilic. So look at this, it's 1,000,000 times more reactive here when you've got a nitrogen lone pair that's really souping up the reactivity of that, sorry for that, when you're souping up the reactivity of that pi system by having that nitrogen lone pair on there. And what's more reactive than a neutral N? O minus. Alkoxide is more nucleophilic than a neutral amine. If you just look at the pK of water and an ammonium ion and back it out, you'd know that an O minus lone pair is more nucleophilic than a neutral amine lone pair. And so now when you go from an enamine to an enolate, you buy yourself another 100 million fold in reactivity. Boy, these lone pairs on that enolate are so nucleophilic. Let me put a yellow dot on our on our nucleophilic carbon. Boy, that just makes me want to take that enolate and do SN2 reactions, add to carbonyl groups and do aldol reactions, add to enones and do Michael additions. Enolates are fantastic. You will find that a naked enolate and a lithium enolate, those are going to exhibit pretty similar patterns of reactivity. So we'll talk a little bit more about how that lithium atom can impact the mechanism of the reaction. But you'll find people using naked enolate anions, if we're allowed to use that term, and lithium enolates in similar situations, similar patterns of reactivity. So wow, enolates. Why are we talking about enols, enol ethers, and enamines when we can talk about enolates? It's kind of not obvious why we would do that, but it's important to put that into context. All right. How do you make enolates? You don't make them like they teach you in a typical sophomore organic chemistry text. I don't know. They try to convince you that you'd be able to take some sort of a ketone and add a base and then deprotonate in some kind of a selective manner on one side or the other. That's not going to happen. That's never going to work well. Let's go ahead and talk about what happens if we take a base. And you may not be familiar with this trityl anion. That's a carbanion with 3 phenyl groups. It's a pretty standard reagent. This looks like it was done in the 1950s or 60s. It's 60s. Nobody uses trityl anion anymore as a base. We have fancier bases that are very aggressive. They just needed a strong base that would thermodynamically drive formation of enolates and leave a potassium counterion here. Let's take a look at the relative regioselectivity here. So if I take some sort of a powerful base, and in this case that's this trityl anion, and we deprotonate, you're going to get deprotonation on both sides of this carbonyl, right? There's H's over here on this side, there's H's over here on this side, and that trityl anion is going to deprotonate on both sides. And so when you look at the product ratios here, it's not selective. Well, it's a little bit selective, 60-40. Nobody in the world wants a 60-40 ratio of 2 different products. That means when you form CC bonds using that as a nucleophile, you get 2 completely different products. That is not a useful selectivity. Unfortunately, there's some sort of an attempt to convince you that you can use that and that the major enolate here, the more substituted enolate, is somehow going to be good. In practice, this is not really widely used. Now, why is it not possible to make one or the other of these? The problem is that under these kinds of conditions, we would refer to this as thermodynamic control. And we'll contrast that with kinetic control. Thermodynamic control, the more stable product is the one that's favored. Under these conditions, the 2 products are equilibrating as you form them, and you can't stop that. Let's go ahead and talk about what's that mechanism for equilibration. If they're equilibrating, the relative ratios of those 2 products is determined by the relative stabilities. So let's first talk about the mechanism for equilibration. Once you start to deprotonate using this trityl anion, this weird-looking trityl anion, I don't think we'll ever see this again in this course, but once you start to deprotonate, right, the first time you make an enolate on one side or the other, the problem is you're still going to have leftover unreacted ketone. This species right here, your starting material, still has H's on there, on both sides. And that can act as that, well, let me be a little bit more, that can act as a sort of conjugate acid in the system that can serve as a proton source. You make your first molecule of enolate, but you're still going to have proton sources that can catalyze protonation. And what does an enolate do when you put it in the presence of a proton source? It protonates. So the second you make an enolate while there's still starting material around, you're going to start to see this happen. You're going to start to see that you pick up a proton, and now the base that's still present, any basic species, like another enolate molecule, can pull a proton off the other side. And this is all in equilibrium. You can't stop this from happening under these types of conditions. If you use trityl anion or potassium T-butoxide or sodium hydroxide, it does not matter. Those are equilibrating conditions. And so you will get, because of this facile equilibrium here, you will get an equilibrium ratio of the enolates in solution. Yes, question? Yes, sodium hydride is not a powerful base. So the second one sodium hydride comes along and pulls off a proton, you still have 10 to the 23rd acids. The ketone itself is an acid. You have 10 to the 23rd proton sources still waiting around as the sodium hydride slowly dissolves and slowly deprotonates. All of this stuff is floating around ready to act as your proton source. So, what you need in order for this to not be equilibrium conditions is you need a base that is instantaneous and we'll talk about that in just a second. So alkoxide, hydroxide, sodium hydroxide, you're going to get equilibrium ratios of these two enolates. Now, okay, 60-40 is not great, but we could have predicted ahead of time which of these would be favored. That's easy to predict, that one of these would be a bit favored more than the others. You get, when you do equilibrating conditions, you get the more substituted enolate. The more substituted enolate is favored under equilibrating conditions. More substituted. That's just like alkenes. If I take these three alkenes down below, they all have the same number of carbons and hydrogens. All I'm doing is moving the double bond around to different positions. Same molecular formula, same number of C's, same number of H's. They're not equally stable. We have this general idea in organic chemistry that more substituted alkenes are more stable. If you throw in catalytic sulfuric acid, you can isomerize those double bonds around. And what you would find is that the relative stabilities of these is that the more substituted alkene is more stable, just like the more substituted enolate is more stable. Why is the more substituted alkene more stable? Because you want to have some sort of resonance with these donor bonds donating into pi star. That stabilizes the system. The molecule's more stable. The more CHs you have, allylic, or bonds that you have allylic, the more stable that alkene will be. So enolates are just like alkenes. More substituted enolates are thermodynamically more stable than less substituted enolates. Okay, nobody wants mixtures, so this is why people weren't using enolates back in the 50s. They were using enamines because they had a way to prepare one regiochemistry of enamine over another. But we found a way around this, right? Late 1960s, early 1970s, revolution in the field of enolate chemistry. Somebody found a way to perfectly control the regiochemistry of enolate formation, and that was under these conditions right here. LDA, inverse addition, THF, minus 78 degrees. You need those three sets, those variables, LDA, inverse addition, and minus 78. And when you do that, what you end up with is a 100 to 0 ratio of the less substituted enolate. 100 to 0. Is it 0.5 or 0.01? I don't know. It's 100 to 0, right? Man, now that is useful. What's going on here? What's the secret with this? So what does inverse addition mean? Inverse addition means you don't start off with the ketone in your pot. Inverse addition means you start off with the LDA in your reaction mixture. You have an ocean of LDA, lithium diisopropylamide, and you are slowly dripping in the ketone. Slowly dripping in ketone to a vast ocean of LDA. And so every single drop of ketone that hits that solution, let's go ahead and take a look at the mechanism. What's the mechanism for deprotonation of LDA? Take a look at this reagent. What's the reactive part of this reagent right here? Well, it's not the lone pair yet. It's the lithium atom. Lithium wants 8 electrons, just like carbon. If I drew a carbon atom that had 1 bond, you'd say, whoa, that's not good. I want to have 4 bonds to carbon. Lithium's the same. Lithium wants 4 bonds on it. So the first thing I'm going to do is I'm going to take this lone pair, and I'm going to add it to the lithium. That is step one. Carbonyl groups, it attacks that lithium atom. Lithium wants 8. Now there are solvent molecules. THF has oxygen. They're trying to bind to that. They're coming on. THF molecules are adding and coming off of that lithium. But eventually, the second a carbonyl adds, you're dripping carbonyls into an ocean of LDA. You're keeping the temperature low. And under those conditions, we end up with this like magical structure here. Let's go ahead and draw out that magical structure. Now it's O+. So now that carbonyl is more reactive, and it is lithium minus. That means that this nitrogen and the lone pairs on the nitrogen are more basic and more nucleophilic. That lone pair is now souped up because of that lithium minus next door. And if I come over here and I draw this proton at the alpha position, it's easy to see 6 atoms away why that nitrogen wants to pull off that proton. Now that we have O+ on the other side, it is super easy, unstoppable for you to take this proton off and push the electrons into this carbonyl that's now O+. Boy, that is satisfying. It's intramolecular, 6-membered ring. I've got an O+ that makes the carbonyl more reactive. I've got the lithium minus that makes the nitrogen lone pair more basic. There's just this amazing acceleration, and this is fast at minus 78 degrees. And what's powerful about this process and what makes this such a mainstay for modern organic synthesis is it's not just a matter of regiochemistry. So you can be guaranteed, so let me just draw it in case you've forgotten what is LDA. Lithium diisopropylamide has 2 isopropyl groups on there. Not 2 ethyl groups, not 2 T-butyl groups, not 2 methyl groups. They tried every single combination in order to find out which one was just right. And it turns out that 2 isopropyl groups are just right. Those isopropyl groups are critical for this reaction. Those isopropyl groups are bulky, and they ensure that you deprotonate on the less hindered side instead of the more hindered side. T-butyl, too bulky. Methyl, not bulky enough. Isopropyl, perfect. Lithium diisopropylamide. So this 6-membered ring goes through a chair-like transition state. So let's go ahead and draw out that transition state. I've kind of sketched out at the bottom here the outline of a chair. Hopefully, I would hope that you would be good at drawing chairs, practice drawing chairs, but not just drawing chairs where we can clearly see the axial and equatorial substituents. And notice when I draw a chair, I make absolutely sure that this carbon and this carbon are not right on top of each other. I've practiced a lot drawing chairs because I practice to make sure that when I draw 2 axial bonds, they are not overlapping. Right? If you end up with 2 axial bonds overlapping, nobody will be able to see anything when you draw out your chairs. So let's go ahead and draw out these pieces here. You know, I could position the pieces of this chair any way I want. I'm going to put the oxygen bond of that carbonyl in back, and I'm going to go ahead and put this carbon bond, the alpha carbon we're deprotonating, up front. And when I put the ethyl group on here, the methyl group, this methyl group over here. When I put this methyl group on that alpha carbon, I have a choice. Do I want to have an H? Well, let me put the H that's being deprotonated. There's the H that's being deprotonated. So I've got now a methyl group over here. I want the methyl group to be equatorial. I do not want the methyl group to be axial. This carbon right here, that stays sp2 from beginning to end. So I'm going to draw the bond at an angle that's somewhere between axial and equatorial. That's that ethyl group on the other side of the carbonyl. And so now when I draw that basic nitrogen in, the one that's deprotonating, it's coordinated to a lithium I'm going to draw in the back. And now I have these bulky, bulky, bulky isopropyl groups. Bulky, bulky, bulky. Not too bulky, but just the right bulk. And because of those isopropyl groups, when I position the methyl group and the H, I'm never going to put the methyl group axial. Because if I try to put the methyl group axial, right, I'm trying to minimize that steric interaction. I'll just write minim. Minimize that. You want to minimize that steric interaction by putting the H up and the methyl down. And so because of that transition state, let me put the charges there. This is kind of a transition state with dash bonds. Let me finish up putting some dash bonds in here. So if I can fit them in. So we're breaking the carbonyl, we're forming an enolate anion. And so in this product, we end up pulling off a proton and stereoselectively generating an enolate that has a very specific geometry. And that geometry now has this methyl group on the opposite side of the oxygen. And the H will be on the cis side next to the oxygen. So that's the structure of the next intermediate in this deprotonation step. Now, it's quite common to show the amine dissociating from the Li minus, right, and then just leaving behind the lithium. If you left it on there, you'd be doing a more accurate job of describing what's going on in solution, but it's very common to dissociate when you draw the arrow pushing mechanism. I'm fine if you do that. Right, let's take the electrons and give them to the N+. And notice that you get a very specific geometry of the enolate. So the methyl group ends up, the bulkier group ends up opposite from the oxygen. And the less sterically hindering group, which is usually an H, ends up on the same side as the oxygen. Because of that chair-like transition state. Because somebody was very clever to find that isopropyl groups give you that bulk in that chair-like transition state. Okay, this is called the Ireland transition state. Robert Ireland explored this stuff in the 70s, I think late 70s, early 80s, and it revolutionized enolate chemistry. Now we can make one enolate and only one enolate with a very specific geometry, and that's really powerful. Enolates are super useful reactions. Now, what do you do with a lithium enolate? You make carbon-carbon bonds. Boy, the lone pair, that enolate is super nucleophilic. And where is it nucleophilic? It's nucleophilic right here. If we were saying that enols and enamines were nucleophilic, this lithium enolate is going to be really nucleophilic, powerfully nucleophilic. But I've run out of time. My God, I wanted to show you this, but I've run out of time. We're going to have to talk more about the aldol reaction with lithium enolates when we come back. It's going to involve chairs again. And it's going to be super selective. And it's going to be the way we do modern organic synthesis.